In computability theory, primitive recursive functions are a class of functions that are defined using primitive recursion and composition as central operations and are a strict subset of the total µ-recursive functions. Primitive recursive functions form an important building block on the way to a full formalization of computability. These functions are also important in proof theory. Most of the functions normally studied in number theory are primitive recursive. For example, addition, division, factorial, exponential and the nth prime are all primitive recursive. So are many approximations to real-valued functions. In fact, it is difficult to devise a total recursive function that is not primitive recursive, although some are known. The set of primitive recursive functions is known as PR in computational complexity theory. Definition: the primitive recursive functions are among the number-theoretic functions, which are functions from the natural numbers 0, 1, 2, to the natural numbers. These functions take n arguments for some natural number n and are called nary. The basic primitive recursive functions are given by these axioms. Constant function. The 0-ary constant function 0 is primitive recursive. Successor function. The 1-ary successor function s, which returns the successor of its argument, is primitive recursive. That is, s equals k plus 1. Projection function. For every n1 and each I with one in, the nary projection function pin, which returns its ith argument, is primitive recursive. More complex primitive recursive functions can be obtained by applying the operations given by these axioms. Composition. Given f, aka primitive recursive function, and kmary primitive recursive functions g1, gk, the composition of f with g1, gk, i.e., the mary function is primitive recursive. Primitive recursion. Given f, aka primitive recursive function, and g, aary primitive recursive function, the ary function h is defined as the primitive recursion of f and g, i.e., the function h is primitive recursive when n. The primitive recursive functions are the basic functions and those obtained from the basic functions by applying these operations a finite number of times. Role of the projection functions. The projection functions can be used to avoid the apparent rigidity in terms of the arity of the functions above by using compositions with various projection functions. It is possible to pass a subset of the arguments of one function to another function. For example, if g and h are two ary primitive recursive functions, then is also primitive recursive. One formal definition using projection functions is converting predicates to numeric functions. In some settings it is natural to consider primitive recursive functions that take as inputs tuples that mix numbers with truth values, t equals true, f equals false, or that produce truth values as outputs. This can be accomplished by identifying the truth values with numbers in any fixed manner. For example, it is common to identify the truth value t with the number 1 and the truth value f with the number 0. Once this identification has been made, the characteristic function of a set A, which literally returns 1 or 0, can be viewed as a predicate that tells whether a number is in the set A. Such an identification of predicates with numeric functions will be assumed for the remainder of this article. Computer language definition. An example of a primitive recursive programming language is one that contains basic arithmetic operators, conditionals and comparison, and bounded loops, such as the basic for loop, where there is a known or calculable upper bound to all loops. No control structures of greater generality, such as while loops or if then plus goto, are admitted in a primitive recursive language. Douglas Hofstadter's Blooping Gödel, Escher, Bach is one such. Adding unbounded loops makes the language partially recursive, or Turing complete. Floop is such, as are almost all real-world computer languages. Arbitrary computer programs, or Turing machines, cannot in general be analyzed to see if they halt or not. However, all primitive recursive functions halt. This is not a contradiction. Primitive recursive programs are a non-arbitrary subset of all possible programs, constructed specifically to be analyzable. Examples: most number-theoretic functions definable using recursion on a single variable are primitive recursive. Basic examples include the addition and truncated subtraction functions. Addition. Intuitively, addition can be recursively defined with the rules add equals x, add equals add plus 1. To fit this into a strict primitive recursive definition, define add equals p11, add x equals s, x. Here S is the successor of n, p11 is the identity function, and p23 is the projection function that takes 3 arguments and returns the second one. Functions f and g required by the above definition of the primitive recursion operation are respectively played by p11 and the composition of s and p23. Subtraction. Because primitive recursive functions use natural numbers rather than integers, and the natural numbers are not closed under subtraction, a truncated subtraction function is studied in this context. This limited subtraction function sub, or BA, returns BA if this is non-negative and returns 0 otherwise. The predecessor function acts as the opposite of the successor function and is recursively defined by the rules pred equals 0, pred equals n. These rules can be converted into a more formal definition by primitive recursion. Pred equals 0, pred equals p12. The limited subtraction function is definable from the predecessor function in a manner analogous to the way addition is defined from successor. Sub equals p11, sub x equals pred x. Here sub corresponds to BA. For the sake of simplicity, the order of the arguments has been switched from the standard definition to fit the requirements of primitive recursion. This could easily be rectified using composition with suitable projections. Other operations on natural numbers, exponentiation and primality testing are primitive recursive. Given primitive recursive functions e, f, g, and h, a function that returns the value of g when ef and the value of h otherwise is primitive recursive. Operations on integers and rational numbers by using Gödel numberings. The primitive recursive functions can be extended to operate on other objects such as integers and rational numbers. If integers are encoded by Gödel numbers in a standard way, the arithmetic operations including addition, subtraction, and multiplication are all primitive recursive. Similarly, if the rationals are represented by Gödel numbers, then the field operations are all primitive recursive. Relationship to recursive functions. The broader class of partial recursive functions is defined by introducing an unbounded search operator. The use of this operator may result in a partial function, that is, a relation with at most one value for each argument, but does not necessarily have any value for any argument. An equivalent definition states that a partial recursive function is one that can be computed by a Turing machine. A total recursive function is a partial recursive function that is defined for every input. Every primitive recursive function is total recursive, but not all total recursive functions are primitive recursive. The Ackermann function A is a well-known example of a total recursive function that is not primitive recursive. There is a characterization of the primitive recursive functions as a subset of the total recursive functions using the Ackermann function. This characterization states that a function is primitive recursive if and only if there is a natural number m such that the function can be computed by a Turing machine that always halts within a or fewer steps, where n is the sum of the arguments of the primitive recursive function. An important property of the primitive recursive functions is that they are a recursively enumerable subset of the set of all total recursive functions. This means that there is a single computable function f such that, for every primitive recursive function g, there is an e such that g equals f for all n, and, For every e, the function h equals f is primitive recursive. However, the primitive recursive functions are not the largest recursively enumerable set of total computable functions. Limitations. Primitive recursive functions tend to correspond very closely with our intuition of what a computable function must be. Certainly the initial functions are intuitively computable, and the two operations by which one can create new primitive recursive functions are also very straightforward. However, the set of primitive recursive functions does not include every possible total computable function. This can be seen with a variant of Cantor's diagonal argument. This argument provides a total computable function that is not primitive recursive. A sketch of the proof is as follows. The primitive recursive functions of one argument can be computably enumerated. This enumeration uses the definitions of the primitive recursive functions, and can be assumed to contain every definition once, even though a same function will occur many times on the list. This means that the nth definition of a primitive recursive function in this enumeration can be effectively determined from n. Indeed, if one uses some Gödel numbering to encode definitions as numbers, then this nth definition in the list is computed by a primitive recursive function of n. Let fn denote the unary primitive recursive function given by this definition. Now define the evaluator function, ev with two arguments, by ev equals phi. Clearly ev is total and computable, since one can effectively determine the definition of phi. And being a primitive recursive function, phi is itself total and computable, so phi is always defined and effectively computable. However, a diagonal argument will show that the function ev of two arguments is not primitive recursive. Suppose ev were primitive recursive, then the unary function g defined by g equals s would also be primitive recursive, as it is defined by composition from the successor function in ev. But then g occurs in the enumeration, so there is some number n such that g equals fn. But now g equals s equals s equals s gives a contradiction. This argument can be applied to any class of computable functions that can be enumerated in this way, as explained in the article Machines That Always Halt. Note, however, that the partial computable functions can be explicitly enumerated, for instance by enumerating Turing machine encodings. Other examples of total recursive but not primitive recursive functions are known. The function that takes m to Ackermann is a unary total recursive function that is not primitive recursive. The Paris-Harrington theorem involves a total recursive function that is not primitive recursive. Because this function is motivated by Ramsey theory, it is sometimes considered more natural than the Ackermann function, the Sudan function, the Goodstein function. Some common primitive recursive functions. The following examples and definitions are from Clean pp. 223 to 231. Many appear with proofs. Most also appear with similar names, either as proofs or as examples, in Boulos Burgess Jeffrey 2002 pp. 63 to 70. They add number 22 the logarithm lower LG depending on the exact derivation. In the following we observe that primitive recursive functions can be of four types. Functions for short. Number theoretic functions, from 0, 1, 2, 2, 0, 1, 2. Predicates, from 0, 1, 2, to truth values, t equals true, f equals false. Propositional connectives, from truth values, t, f, to truth values, t, f. Representing functions, from truth values, t, f, to 0, 1, 2. Many times a predicate requires a representing function to convert the predicate's output, t, f, to 0, 1, defined below. By definition, a function phi is a representing function of the predicate p if phi takes only values 0 and 1 and produces 0 when p is true. In the following, the mark, e.g., a, is the primitive mark, meaning the successor of, usually thought of as, +1, e.g., a +1 equals def a. The functions 16 to 20 and #g are of particular interest with respect to converting primitive recursive predicates to, and extracting them from, their arithmetical form expressed as Gödel numbers. Addition, a plus b, multiplication, a times b, exponentiation, ab, factorial a, 0, equals 1, a, equals of times a, pred, if a greater than 0 then a1 else 0, proper subtraction a b, if a b then a b else 0, minimum, maximum, absolute difference, a b equals def plus, tilde sg, not, signum, if a equals 0 then 1 else 0, sg, signum, if a equals 0 then 0 else 1, a, b, if b equals k times a for some k then 0 else 1, remainder, the leftover if b does not divide evenly, also called mod, a equals b, sg, a, b, a less than b, sg, pr, a is a prime number, pr equals def a greater than 1 and not 1 less than c less than a, c, a, pi, the I plus 1 saint prime number, I, exponent of pi in a, the unique x such that pics are not, lh, the length or number of non-vanishing exponents in a, logarithm of a to the base b. In the following, the abbreviation x equals def x1, xn subscripts may be applied if the meaning requires. A function phi definable explicitly from functions psi and constants q1, qn is primitive recursive in psi. B, the finite sum sigma y less than z psi and product pi y less than z psi are primitive recursive in psi. C, a predicate p obtained by substituting functions chi1, chi-m for the respective variables of a predicate q is primitive recursive in chi1, chi-m q. D, the following predicates are primitive recursive in q and r, not underscore q, q or r, qvr, q and r, q and r, q implies r, qr, q is equivalent to r, qr, #e. The following predicates are primitive recursive in the predicate r, y less than z r where y less than z denotes there exists at least one y that is less than z such that y less than z r where y less than z denotes for all y less than z it is true that mu y less than z r, the operator mu y less than z r is a bounded form of the so-called minimization or mu operator, defined as the least value of y less than z such that r is true, or z if there is no such value. F. Definition by cases. The function defined thus, where q1, qm are mutually exclusive predicates, shall have the value given by the first clause that applies, is primitive recursive in phi1, q1, qm. Phi equals phi1 if q1 is true. Phi m if qm is true. Phi m plus 1 otherwise. G. If phi satisfies the equation, phi equals chi x2, xn then phi is primitive recursive in chi. So, in a sense the knowledge of the value not phi of the course of values function is equivalent to the knowledge of the sequence of values phi. Phi of the original function. Additional primitive recursive forms. Some additional forms of recursion also define functions that are in fact primitive recursive. Definitions in these forms may be easier to find or more natural for reading or writing. Course of values recursion defines primitive recursive functions. Some forms of mutual recursion also define primitive recursive functions. The functions that can be programmed in the loop programming language are exactly the primitive recursive functions. This gives a different characterization of the power of these functions. The main limitation of the loop language, compared to a Turing-complete language, is that in the loop language the number of times that each loop will run is specified before the loop begins to run. Finitism and consistency results. The primitive recursive functions are closely related to mathematical finitism, and are used in several contexts in mathematical logic where a particularly constructive system is desired. Primitive recursive arithmetic, a formal axiom system for the natural numbers and the primitive recursive functions on them, is often used for this purpose. PRA is much weaker than µ-arithmetic, which is not a finitistic system. Nevertheless, many results in number theory and in proof theory can be proved in PRA. For example, Gödel's incompleteness theorem can be formalized into PRA, giving the following theorem. If T is a theory of arithmetic satisfying certain hypotheses, with Gödel's sentence GT, then PRA proves the implication con GT. Similarly, many of the syntactic results in proof theory can be proved in PRA, which implies that there are primitive recursive functions that carry out the corresponding syntactic transformations of proofs. In proof theory and set theory, there is an interest in finitistic consistency proofs, that is, consistency proofs that themselves are finitistically acceptable. Such a proof establishes that the consistency of a theory T implies the consistency of a theory S by producing a primitive recursive function that can transform any proof of an inconsistency from S into a proof of an inconsistency from T. One sufficient condition for a consistency proof to be finitistic is the ability to formalize it in PRA. For example, many consistency results in set theory that are obtained by forcing can be recast as syntactic proofs that can be formalized in PRA. History. Recursive definitions had been used more or less formally in mathematics before, but the construction of primitive recursion is traced back to Richard D. Deacon's theorem 126 of his was sind und was sollen die Zahlen. This work was the first to give a proof that a certain recursive construction defines a unique function. Primitive recursive arithmetic was first proposed by Thoralf Skolem in 1923. The current terminology was coined by Roger Petter after Ackermann had proved in 1928 that the function which today is named after him was not primitive recursive, an event which prompted the need to rename what until then were simply called recursive functions.